Well, in this tutorial of real numbers, we are going to look at what is decimal expansion and how decimal expansion basically helps you determine whether a given decimal number is a rational or an irrational number. All right. So there could be three cases of decimal expansion. They have been classified as what you see here: terminating, non-terminating, and recurring, and then finally non-terminating and non-recurring. So what is the difference between each one of those? So let's say my first number is a terminating decimal numbers. These are the numbers such as if I write a number 1.25. There are only finite number of decimal digits in this number, right? And why do I say that such numbers are rational numbers? Because I can very easily convert this decimal number into its fractional equivalent just by replacing those two decimal digits with two zeros in the denominator. And this is very well a form of a number p over q, right? And further, if you would like to convert this number into its lowest form, you could say that 125 can be written as 25 times 5 and 100 can be written as 25 times 4. Now you simply get rid of 25 and the number you obtain finally is 5 over 4, which is the form of p over q, and hence it is classified as a rational number, right? So this is an example of a terminating decimal numbers, right? When you see a finite number of decimal digits in any decimal number. Now let us take a look at the second case, what we classify as non-terminating and recurring. So if I were to write a number such as 1.37, 37, and 37, and then so on, basically the digits, the decimal digits 3 and 7, they continue to repeat forever in this pair 37. So that is why it is called non-terminating, because this decimal sequence never ends, and it is called recurring because you see a pattern of repetition. The numbers repeat themselves, right? That is why we say that such numbers are called non-terminating and recurring in their pattern, right? So we are saying that such numbers are also classified as rational numbers. So let me demonstrate that here. So let's say if I say that this number x is equal to 1.373737 and it goes on forever, okay? So let me now multiply this number with 100 on both sides. So I can say that 100x is equal to 100 times 1.3737 and 37 and so on, all right? You can easily write this number to be equal to 137.3737 and so on, right? Now let me subtract the number x from 100x. So then when you do that, what you obtain is 100x minus x is equal to 137.373737 and so on. And you can write the subtraction here that less 1.373737 and so on. So when you carry out this subtraction, what you obtain on the left hand side is 99x is equal to, and this number gives you very simply 136, because you see this 0.3737, the decimal expansion, it basically negates each other with the one which is in the subtraction, right? And 137 minus 1 is equal to 136. Or in other words, you can say that the x, the number is equal to 136 over 99. That means the number that was originally in the non-terminating but recurring form, this number x can be equated to 136 over 99. And that is nothing but a form of the number p over q. And therefore, we can say that non-terminating and recurring decimal numbers are also classified under rational numbers. Or in other words, both of these categories, A and B, are part of the numbers that are rational numbers. Okay. Now, what are the examples of non-terminating and non-recurring? So let us take a look at that with the help of this example. So let me write an irrational number. Let's say I take a very common example of an irrational number, that is pi. And pi, we know that it is equal to 3.14159 and then it goes on forever, right? We don't know what is the end of this decimal sequence. So that is why we say that this is a kind of a number which is classified as non-terminating and it is non-recurring. Now, you will say that why can't we apply this method that we just learned here into these kind of numbers and see that can we really convert such numbers into the form of P over Q. Okay, I would say not, but let's prove it. Let's say if I multiply this with 100 and I say that 100 pi is equal to 100 times 3.14159 and it goes on, right? Or you can say that with this 100 in multiplication, it can be written as 314.1519. So you will say that just like what we did here, what if we were to subtract 1 from the number 2, then you will say that we will obtain 99 pi on the left hand side, but the right hand side will contain 314.159 minus 3.14159 and so on. But if you were to carry out this subtraction, you will not obtain any meaningful result, because even though you will say that on the left hand side I have obtained 99 pi, but this is equal to some number which is, let's say, 311 point some numbers here, and those numbers could be 0, 1, 2, 3 and whatever it is, right? Basically you are not able to get rid of this decimal part. You have obtained one another series of decimal numbers here which you do not find an end to it. So if you cannot get rid of this decimal part, you can never convert this number pi into its form of P over Q. You just can't, right? And that is why we say that pi is a number which belongs to a category of non-terminating and non-recurring. So therefore you will say that just like what we stated above, when we classify our numbers into a category of the numbers that are non-terminating and they are non-recurring, then those set of numbers can be classified as the irrational numbers. So this is the idea of decimal expansion, that decimal expansion could exist in three forms: terminating, non-terminating and recurring, and non-terminating and non-recurring. Out of those three, the third one, which is non-terminating and non-recurring, is a category of the numbers what we define as irrational numbers. So with that, we will take a pause here, and in our next tutorial, we will learn a little bit more about performing operations, the mathematical operations between the rationals and irrationals.